Hi, my name is Jerry Abraham. Today we'll take a deep dive into the RAG architecture and hopefully over the next few minutes uncover what really happens under the hood. RAG stands for Retrieval-Augmented Generation. But here we need to just pause and understand what are large language modules or LLMs. LLMs like GPT and BERT are trained on huge sets of data but can hallucinate and miss updated information. So RAG allows them to look at external data like documents, PDFs, and private data so that we can have more accurate, factual, and grounded answer. So RAG uses this and combines this with the generative capabilities of LLMs to produce responses that are more conversational, contextual, and accurate. How RAG works. This slide gives us a 30,000 feet view of how RAG works. So you have the retrieval, augmentation, and generation phase. In the first phase, the user actually asks a bot a question and RAG retrieves the relevant chunk from a vector database. This is based on cosine similarity. These chunks then move into the augmentation phase. These chunks get appended to a prompt. From here, it moves to a generation phase where the LLM takes this input and gives a final answer. So this answer is more human centric and which is more contextual and factual in content. In the industry, typically, let's say banking and insurance, they use Azure OpenAI plus RAG. Startups use OpenAI API plus RAG. Government and defense organizations would use private LLMs like Llama, Mistral. Hugging Face has Bloomberg. Interestingly, it's an open source LLM. Meta or Facebook has LLMs like Llama 2, 3, and Google AI has BERT. One would ask, why not just use retrieval? Why add generation, right? So when you have all your knowledge base in the retrieve phase, why do you want to use generation? Let's try and understand that better. So let's say a user asks a query, I want to close my home loan. Can someone else authorize it for me if I'm not available? So if it's a retrieve-only phase, you have chunks retrieved from the vector database, and you will have two sets of information, which looks like this. To close your home loan, visit nearest branch with original documents, loan account statement, and ID proof. Then you have the other chunk, which would say, if you are unavailable, you may authorize a representative by providing a signed authorized letter, valid ID, and original document. Now, if this was to be a simple FAQ, then it's fine. It serves the purpose. But here, that's not what we're looking for, right? So the user will actually have to look at all this information and try and interpret that. But when it comes to RAG, you have retrieval plus LLM. So the response would look something like this. Say to close your home loan, visit your nearest branch with your documents and ID. If you are unavailable, you can authorize someone else with a signed letter, your documents, and other ID. Right? So it combines all the factual information and gives us more flow, clarity, and a more human centric and contextual response. So that is the advantage of using a combination of retrieval plus LLMs. Now, before we go to RAG, there is a pre-processing phase where you actually create your vector database. Let's try and understand that from these next few slides. So you have your offline knowledge, which is your internal data, PDFs, Excels. All these are essentially, all large documents and also, large amount of data. This data then moves into what is called as chunking phase, where they are broken into smaller sections or chunks. Now, one may ask, why do we have to do that? So there are primarily two reasons. One is because of downstream limitation. So in the embedding phase, the model context limit is one of the constraint. So for example, models like BERT can create only 512 tokens and OpenAI embeddings can generate only 8,191 tokens. So this is your text embedding ADA002. Secondly, chunking also helps us to preserve semantic quality. So these are the primary reasons why we have smaller chunks, right? And the end-to-end flow from the beginning to the end is the entire pipeline is managed by orchestrators like LangChain, Llama Index, and Haystack. These are some of the orchestrators that are used in the industry. Now, let's move into the embedding phase. In the embedding phase, you have models like BERT, GPT, Mini, LL. Here, there are two things that actually happen. One is tokenization, where the text becomes a token ID, essentially integers in a list. And the second is the embedding phase, where the token IDs become vector. Here again, there are three embeddings. One is a token embedding. Essentially, here the meaning is captured. The meaning of the words are captured in token embeddings. To this, you will add positional embeddings. This would essentially capture the order of the words. Now, if there is more than a sentence, right? Let's say there are two or three sentences, then those sentences or segments are also embedded, which actually tells you that sentence A is followed by sentence B and sentence B is followed by sentence C. So that is what actually happens in the embedding. Let's actually look at this example and try and understand embedding better. So for example, if you have an input text like I love NLP, this moves to a tokenizer, like let's say a BERT tokenizer, right? So you would have special tokens, which tells you the beginning of the sentence and the end of the sentence. From this, it moves into a token ID. Essentially, you will have a integer, right? So all of these are integers in a list. This then moves into BERT embeddings, where you have a token embedding, segment embedding, and positional embedding, which I spoke about earlier. So these embeddings are essentially an array. It's a vector in a 768 dimension. So to understand this, let's talk about a three-dimensional space, your x, y, and z axis, which goes your x into the positive and negative direction, and so also the other axis. So any point in that space will actually give you. So for example, if it is 1, comma, -1, comma, 1, it just tells you the x, y, and z, right, position. So it tells you where it is located in that space and in which direction it is moving. Now, think about this in a 768 dimension. So that is what it is. So this actually tells you where this point is in that space. So if you have more points closer to that, those becomes its neighbors, or we say those are similar in nature, right? So if you have something in a particular space, anything close to that are those neighboring points. One of the things that you have to understand over here is BERT will output one vector per token. So for example, if you have 7 tokens, you will have 7 tokens getting outputted as 7 vectors into 768 dimension. So just remember that, right? So these embeddings, which are the final embeddings, will move into a BERT transformer encoder layer. And finally, what you get as an output is a number of tokens into 768. So if you have 7 tokens, like I said, which is one vector per token. So you have one 768 dimension vector per token, which is an output. Now this has to go into a vector database like Pinecone or FAISS. But this has to become a single vector, right? That is what is typically taken by your vector database. So the matrix is then reduced to a single vector by using pooling. And this is done by LangChain or Haystack. So what is finally sent into the vector database is your single vector along with the metadata, which has all the information about that vector, which is your page number, source, original text, and all of that. What we have to understand over here is BERT is a sequence encoder, not a sentence encoder. It returns per token embeddings, and you have to pool them. That is why you would want to get this single vector. Now, when you look at your vector database, this is what is actually stored in your vector database. You have your unique ID, you have the single vector, you have the metadata information. So this vector is your exact coordinate in a 768 dimension space. What you also have to understand is, unlike relational database, which is built for structured row and columns, Vector database is built for unstructured data like documents, emails, audios, videos, right? And the indexes are automatically created, but you can also control them with IBF and HNS, which are ANN algorithms, which stands for approximate nearest neighbor. So, what is the rationale behind indexing in a vector database? So, vectors are indexed based on their position in a high dimensional space. So, similar vectors are placed close together. The logic is distance based, not alphabetic or random based, right? So, I hope we are clear so far. So, we have completed the pre-processing phase, right, where you have your vector database that is created. Now let's actually understand the RAG architecture. Now we are in the retrieval phase, right? So the user sends a query to the bot. How does a bank calculate credit risk? Right? This then moves into embedding, right? We said in the embedding, you get a vector, right? This has to become a single vector eventually because you see the number of words you will have your special tokens, token ID, and the embeddings that are created here, token embeddings and positional embeddings. This is just one sentence, so you will not have your segment embeddings. So you have a query vector, which is essentially a point in that 768 dimension, right? Now this then moves to a vector database where the search is based on the ANN algorithm. Like I said, this which stands for approximate nearest neighbor. We will try and look at these two algorithms, and here we will look at two parts. One is how is the indexing done, and second is how is the search done. Now the indexing is done in the pre-processing phase, but as we look at these two algorithms, IVF and HNSW, we will also try and understand that. Right, so in the inverted file index or IVF, typically what happens is it is all the entire vector database is broken into clusters, right? So this clustering is based on k-means algorithm, right? So k-means is used for your clustering and you create centroids based on that. So you have those which are similar vectors which are clustered together and centroid gives a central point. So your vectors, each vector is assigned to the centroid based on distance, and the distance calculation is based on either cosine similarity or Euclidean distance. Okay, now based on this, you will actually build an inverted index. So for each centroid, it will store a list of vector IDs. So your centroid is what actually holds the index. Why do we call this inverted index? Let's try and understand that. Now look at this example below. Say for example, you have, for instance, you have doc 1 which holds this list, banking, loan, regulation, and doc 2 holds a list, policy, loan, and fraud. Look at this, it gets inverted over here and we are saying loan. Okay, so the actual information is over here, right? Now let's look at how that corresponds with us. The actual information is in the vector, right? So the vector space actually holds the information, but we are mapping that to the centroid. So we're saying that is an inverted index. So the IVF index is a lookup table that maps each centroid to a list of vectors assigned to it. So yes, the centroids are keys in the index and the associated inverted list as the vector ID or the actual vector, which are the values. I hope we are clear so far. Now that we have done with the indexing phase, let's move to the search. Right, in the query search, so we've seen that the query has actually become a query vector. So that is again a point in a 768 dimension. So this will try and look at what are my nearest centers, and it will use something called as the Euclidean distance, right, or the cosine similarity. So based on that, it will identify the top n centroids. Now that is identified the top n centroids, it will start looking at into each of those clusters, and then it will identify the top k vectors based on the cosine similarity. So those whichever has the highest cosine similarity is then selected, and then that gets moved to the next phase. So we saw the indexing and also the query. Let's now also look at how the HNS algorithm, HNSW algorithm is structured. Before we understand the hierarchical navigable small world, we need to understand two concepts. The first one is the skip linked list. Now, the skip linked list is essentially about the layers. Okay, you see layers over here, layer 0, layer 1, layer 2. So in layer 0, you will have fewer nodes. These nodes are vectors, right? So each node that you see over here represents a vector. So your lower nodes would will have more so your lower layer rather would have more nodes. As you keep moving up, you see the number of nodes reducing. So that is why you have a skip happening. So we will appreciate this better when you see how a query navigates through a query vector navigates to the to this through this to get to the top k, right? And now to also understand how does what is the concept of navigable small world. In the navigable small world, we actually talk about two things: the links, or what is called as connections, the short paths. So every node is connected to nearby nodes. Plus, there are also a random long range connections. So these act as shortcuts across long distance parts of the graph. So in this graph, you will have short links and you will also have long links. So if you look at this, you will typically have long links in your topmost layer, and you will see how that helps us better in navigation. I hope we are clear so far. So each node is a vector, and it's connected to m nearest neighbors. So m actually tells us the number of outgoing connections per node, right? So M will tell you, for example, how many friends can I have? Let's say if I can have, let's say 16 friends. So these neighbors are based on Euclidean and cosine distance. There is also something called as EF construct, which gives us search width. So if we are saying M tells us that we can have 16 friends, EF construct will tell us how many people you need to interview to have those 16 friends. Okay, so the higher the value of M, it becomes more dense. Lower the value of M, it is more sparse, right? So that is how this works. So HNSW uh, combines the navigable small world and skip linked list. Now, in this particular graph, we will look at the layering logic and also the search strategy. So the layering, every node, right? So if you have a node 1 here, you may not have it here. Node 5 may be here, and here it may not be in the topmost layer. So the layering is decided based on an exponential distribution, right? And most nodes would be there in the layer 0, and as you keep moving to the up layers, you will find that they reduce, right? Now the indexing is a combination of the vector plus connection plus the assigned layers. Let's see what that looks like. Okay, so here is a JSON representation of what an index would look like. So it will have the unique ID, it will have the vector. This tells you how many levels are there, and in each of those levels, okay, what are those neighbors? Okay, so this is what your index actually looks like. So the index is your vector plus the connections plus the assigned layer. So a query would typically start, right? Now this is your search strategy. The query would typically start with the top layer. That is how it starts. It looks at the most recent insertion. So what is the most recent insertion of the node? And it will look at from there, it will start becomes a starting point and then goes to the nearest neighbor. And if it's exhausted, then it moves to the next layer and it keeps moving till the bottommost layer. So the final search at layer 0 will give us the top k nearest neighbor, which are similar vectors. Now this is based on cosine similarity. So that is how you will get your top k vectors. So this actually gives you what the final output looks like, right? So you have your top k. So let's say if k is 5, then you will have your 5 chunks. So you have your ID over here, then you have the cosine similarity score, and then you have the vector, you have the metadata. Okay, so now you've actually done the retrieve part. This then moves to the augmentation phase. In the augmentation phase, you will have all five chunks, right? All five chunks plus the user query. To this, you add system instructions. So this is the additional element or the additional layer which is used for prompt construction. So this actually tells the LLM what is the role that you're playing. So let's read this. You are a financial analyst assistant. Answer the user question only based on context provided. Do not guess if the information is not in the document. Reply with I don't know based on the available data, right? So it will use all the contextual information, the user query plus the system instruction. This is then moved to the LLM. So this is the final augmented prompt that is sent to the LLM. Now here what we have to understand is all of these five chunks. So if K is 5, all 5 will go. All this information, primarily what goes is the some part of the metadata, and also, so you will not have all this vector and all going there. You will have the text, right, from all the five chunks and some part of the metadata, which will give some context to the LLM. Now we are in the generation phase. So the LLM receives the system instruction, which is you are a financial analyst, plus it receives the context, right? All the five chunks plus the user query. So the LLM processes the input, it reads the system instruction, reads the retrieve chunk, reads the user query, and synthesizes a coherent natural language answer. So you get your final output. So that is what is seen by the end user, right? So this is the end-to-end view of the RAG architecture, right? So you have pre-processing, you have the retrieval, augmentation, and generation phase. So you have orchestrators like LangChain, Llama Index, and Haystack, which manages the pipeline. It handles the document ingestion and chunking, embedding, vector storage, query time retrieval, prompt construction, LLM calling, an optional tool and agent reasoning. Right? Let's look at two use cases in banking, right, and try and understand this better. So the first one is the credit risk or loan officer assistant, essentially a bot. So it will retrieve underwriting policies, approval matrices, and scoring guidelines. So here is a user asking a question. Can we approve a personal loan for a 19-year-old student? So the rack pulls from credit policy and then it gives those set of chunks to the LLM, which explains the age restriction and the exception. So you have your data sets over here in the vector database, so related to your credit policy books and loan documentation, and your stacks. These are your embeddings and your LLMs, right? Here is the next example. This is about a retail product query handler, helps customer or RM staff with product related questions. So here a user is asking, what are the interest rates for NRE fixed deposit about 2 crores? So the RAG pulls from the FD rate and policy, LLM answers with relevant rates. So your data is related to your FD rates, all of which sits in your vector database like Pinecone and FAISS, and there are others as well. And the LLM like GPT and all, or would actually look at all this information and based on the prompt, give a structured response to the end user. Yes, so that brings us to the end of our presentation. I hope you have managed to get a better understanding of the RAG architecture and of what really happens under the hood. I have thoroughly enjoyed this time sharing my knowledge with you. Thank you so much for your time. Appreciate your patience. Cheers. Bye bye.